Okay, we're back. The band is amplified and we're ready for the sound check. So let's get to it. Dave, it seems like we're dealing with a lot all at once when it comes to the sound check.
Well, we've basically got the entire system up and running. So there's always technical issues of some sort, whether it be grounding problems, bad cables, broken connectors. So you can always count on there being a problem that you're going to have to deal with.
And this is the point where the mixer plays a critical role.
Absolutely.
Now, when we talk about the console, the desk, the front of house, we're referring to the same thing, right?
Yes, we're talking about the mixer. But usually, a mixer with 12 channels or less is known as a board, and a mixer with 30 channels or more is known as a console.
Because the mixer is the main tool the sound engineer uses, it's essential to understand the basics of what it does and how it does it. So let's go to another session of Sound School, and we'll come back to the sound check when we're back. Without a doubt, the main console or mixer is the brain of any sound reinforcement system. Its primary purpose is to mix, control, process, and route the signals fed into it. Here's a 16 by 8 by 2 console. The 16 refers to the number of channels, the 8 refers to the number of submasters, and the 2 refers to the number of master outputs. Essentially, in this mixer, 16 inputs are mixed down to 2 master outputs left and right. As an added feature, this console also has 2 stereo input channels. Notice in the input section of the mixer that all 16 input channels are identical and contain the same controls. Each input channel or fader strip will commonly have a submaster assignment section, a pan control, input level controls, an EQ section, an auxiliary control section, the channel's volume fader, and a channel pre-fader listen or cue switch. Let's take a closer look at these controls starting from the top. These submaster assignment buttons allow the engineer to group or submix any of the 16 channels by assigning them to one of the 8 submaster outputs. For example, many engineers find it much easier to control the overall volume of multiple drum channels using 2 submaster faders. This is done by assigning each channel's submaster in the channel's submaster assignment section to a submaster pair, for example, submaster 1 and 2. Raising faders 1 and 2 in the submaster section would then control the output level of all channels assigned to submaster 1 and 2. Doing this makes it much easier, for example, to control the entire drum kit's volume from 2 faders instead of 8. Below the submaster assignment switches is the pan control, which controls the placement of the signal of the input channel within the stereo image. The controls in this section deal with the input of the signal you're bringing into the channel. First is the 48-volt phantom power on-off switch. Remember our discussion about condenser mics needing separate power? Here's where it's done on the mixer. If you were using a condenser mic on this channel, you'd turn this switch on to power the mic through the mic cable. Otherwise, it would remain off. The next switch is the 26 dB pad. When this switch is on, it reduces the incoming signal by 26 decibels so the input is not overloaded. You'd use this if adjusting the trim control wasn't enough to prevent the input from being overloaded. Here are the mic and line trim controls. These controls are used to raise or lower the input gain of the signal coming into the channel. Typically, mixers allow you to select between 2 types of inputs, mic level and line level. Use the mic input if you're plugging in a microphone or direct box using an XLR connector. Use the 1/4-inch line level input for devices like a CD player or effect boxes. These first several controls work together depending on what the input is. For example, if you were connecting a vocal mic to this channel, you'd select mic, then adjust the gain or trim control. If the signal was too hot, you'd depress the pad, which would reduce the volume by 26 decibels and allow you to increase the gain control. Next is the phase reverse switch. This allows the polarity of the mic connected to that channel to be reversed. This is useful when you have 2 mics in close proximity, for example when you're miking the snare from the top and the bottom. Because each microphone is receiving different amplitudes of the same wave, there can be cancellation of certain frequencies. We call this destructible interference, and the result can be a thinning of the sound when the 2 mics are blended at the console. The solution may be simply to reverse the phase of one of the mics, creating an in-phase amplitude. Next is the EQ section of the input channel. Generally speaking, all equalizers perform a similar function. That is, they're designed to affect a frequency or a range of frequencies within the audio spectrum. Basically, this is done with a circuit inside the EQ which acts as a filter. The EQ circuit is designed to filter out the frequencies other than those it's meant to affect. It's this aspect of the design of equalizers which makes them useful. You can control and make changes to just a particular frequency or a group of frequencies within the audio spectrum. Equalizers are at work everywhere within a sound system. You may have a 1/3 octave graphic equalizer on the house mains. On the monitor system, you may be using a 1/2 octave fixed EQ. The EQ section of your audio mixer probably contains shelving EQ, semi-parametric, or even fully parametric EQ. The tone controls on the bass player's amplifier may be a 4-band EQ. Equalization lies at the heart of sound reinforcement, and it's important to become familiar with equalizers and how they work. Let's take a closer look at the audio spectrum as it relates to frequency. The audio spectrum is a range which spans roughly 10 octaves. Think of these 10 octaves as the keyboard upon which all of the sounds heard by the human ear are played. The octave represents a proportion of 2 to 1. In other words, one end of the octave is double the frequency of the other end. It's these proportions between different frequencies that our hearing process recognizes, rather than the actual number values between frequencies. As an example, the middle of the audio spectrum is not numerically halfway between 20 and 20,000 or 10,000 10. Rather, it's half the number of octaves from 20 to 20,000. And since there are 10 octaves in the audio spectrum, 20 to 40 being the first, 40 to 80 the second, 80 to 160 the third, and so forth, the fifth octave, or approximately 640 Hz, is the middle of the audio frequency spectrum. The audio spectrum can also be evenly divided into 3 decades, which in audio language refers to the number of frequencies falling within a ratio of 10 to 1. The first decade has a span from 20 Hz to 200 Hz, the second decade from 200 Hz to 2000 Hz, and the third decade from 2000 Hz to 20,000 Hz. This can be a useful way of dividing the audio spectrum, because individual speaker components in many sound reinforcement applications are inherently limited to about 1 decade of effective frequency range. A 1-octave fixed frequency EQ has 10 bands. Each band corresponds to a doubling of the center frequency starting at 20 Hz. A 1/3 octave fixed frequency EQ typically has 31 bands. This means there are 3 frequency point subdivisions between each octave, or center frequency doubling. The more subdivisions there are between the frequency doublings, the finer the EQ control which can be achieved. So what do equalizers do exactly? Generally speaking, equalizers allow the user to cut or boost frequencies or ranges of frequencies in specific areas of the audio spectrum. This graphic equalizer is called a fixed frequency EQ because you're cutting or boosting frequencies at preset areas of the spectrum. For multiband EQs of 10 bands or more, these center frequencies have been established and standardized worldwide by the International Standards Organization. From fixed frequency, let's look at variable frequency EQs, sometimes referred to as semi-parametric EQs. Whereas fixed frequency EQs have preset frequency points, variable frequency EQs allow the user to select any frequency point along the continuous frequency range and then cut or boost at that frequency point. Beyond the semi-parametric EQ, a fully parametric EQ adds another important feature. Besides being sweepable, the user can control the bandwidth. The bandwidth is the range of emphasis to the sides of a center frequency point. This is often called the quality factor, or Q, of an EQ filter. Basically, the narrower the Q is set, the closer to the center frequency the cut or boost will apply. The broader the Q is set, the further out from either side of the center frequency the cut or boost will be. Because of the combination of these 3 controls, the frequency, the emphasis or the cut or boost, and the Q, the fully parametric EQ provides the maximum flexibility. Another important category of EQ is called shelving EQ. The standard bass and treble controls common on many instruments belong in this category. Shelving EQ controls affect all frequencies either above or below a particular point in the spectrum. For example, the bass control knob may represent 60 Hz, and the treble knob may represent 10 kHz. Turning up or turning down the bass knob will boost or cut the frequencies below 60 Hz. Turning up or turning down the treble knob will boost or cut the frequencies above 10 kHz. Two other important equalization filters are high-pass and low-pass filters. As the name suggests, a high-pass filter allows only frequencies above a certain approximate point in the audio spectrum to pass. A low-pass filter does just the opposite. It allows only frequencies below a certain point in the audio spectrum to pass. Often, a mixer will include the capability to cut frequencies at either end of the spectrum. For example, this mixer provides an 80 Hz low-cut control. Such a control is actually engaging a high-pass filter, thereby allowing only frequencies above a certain level, in this case 80 Hz, to pass. As a result, the frequencies below this point are rolled off. The most common use for the low-cut switch is to eliminate unnecessary low frequencies from the input channel being used for vocals and treble instruments, such as the hi-hat. Okay, let's get back to our overview of the EQ section on our mixer. It's not uncommon to have several types of EQ in the EQ section of the mixer, including shelving, semi-parametric, and high and low-pass filters. This allows the engineer the most flexibility for shaping and controlling the sound. Here's a high-pass filter. You'd use this filter for vocals or other instruments that don't require strong low end. This is the high-frequency EQ control with shelving, cut, or boost. Next is the high-mid EQ with peaking. The upper control selects the center frequency, and the lower control varies the amount of cut or boost. Next is the low-mid EQ with peaking. It operates exactly as the high-mid but with a different center frequency. Then, the low-frequency EQ with shelving, cut, or boost. Below the EQ section on down the channel strip are the auxiliary sends, or aux sends for short. The signal from the aux sends arrives at separate aux outputs. These allow the engineer to separately adjust the amount of signal, which can be sent to devices other than the main amplifiers and speakers, such as monitor amplifiers or effects units like reverb and delay. When the pot of an auxiliary send on a channel is turned up, the signal is fed into a bus wire inside the mixer. A bus is a way of carrying a group of individual signals along a common route, just like a bus would carry passengers to a common destination. Here, though, the destination is a combining amp, also known as a summing amp. The sum amp inside the mixer puts out a signal which represents the combination of all signals fed into that specific bus. In this case, the aux bus. An aux master control then determines the overall output gain of the auxiliary mix. Another example of a bus is the main mixing bus. All the channel faders feed their signal into one main mixing bus, which is summed and arrives at the main output of the mixer after control by the main fader. Aux sends can be pre-fader or post-fader. Pre-fader means that the aux send will draw its signal copy before the fader, and the fader or EQ won't affect the signal. Post-fader means the aux send draws its signal copy after the fader and EQ, and will be affected by the adjusting of these controls. Typically on a mixer, some of the aux sends are pre and some are post. On this mixer, aux 1 and 2 and 3 and 4 are selectable between pre or post fader. Aux 5 is permanently post, and aux 6 can be either post or direct. Direct means the aux send can be made to control the direct output volume of the channel. Usually, aux sends sent to effects units are post fader, while signals sent to the monitors are pre fader. This is because the normal expectation is that effect units will receive a signal similar to the main mix, which would be post-fader, whereas monitor signals are kept pre-fader to reduce the likelihood of feedback. The channel on-off switch allows the channel to be disengaged when not needed. It's always a good idea to turn off any channel that's not in use in order to keep noise down and guard against feedback. The solo or pre-fader listen switch allows the engineer to monitor the channel through headphones or level check in the master VU meters. The peak overload LED lights up if the channel approaches clipping or overload. The fader controls the volume of the input channel and the amount of gain sent to the main mixing bus. Before starting a sound check, it's important to double check several key input channel settings. Let's go through them quickly. First, check the mic line select and make sure it's selected for the correct input. Remember, for direct boxes and microphones, use the mic select. For line-level inputs such as CD players or effect returns, use the line select. Second, if you're using a condenser mic or a remotely powered direct box, make sure the phantom power switch is engaged. If you're not using a mic that requires power, keep this switch off. Otherwise, you may get a large pop in the system when plugging in a regular mic. Third, make sure to put the aux send for the monitors in pre-fader position if controlling them from the house. Next, Check the panning position in the submaster selection for the channel to make sure the signal is being routed where it needs to go. Finally, start the sound check with faders and input gains at their lowest setting. Adjust the trim control, then bring the channel fader up to a comfortable average setting. Okay, school's out. Welcome back from Sound School. What you've learned about mixers and EQs will really help you as we continue the sound check process. Okay, Dave, what's first?
Well, first I'm going to work on the drums. I'm going to have the drummer play a steady beat on the kick so that I can adjust the input gain, the EQ, and then the noise gate. Go ahead and give me that kick. Okay, stand by.
Okay, so explain what you did.
Well, I put a pad in on the input gain, a 26 dB pad, and then trimmed out the input gain. I adjusted the EQ. I rolled up 3 dB at 5K to get the attack of the kick drum. Then I also boosted 80 Hertz to get the thud and that low-end rumble. Then I adjusted the noise gate appropriately. Here, the filter is set for 20 Hertz to 5 kilohertz with a threshold of -10 dB and a release time of 1/10 of a second.
Dave, what's the function of a noise gate?
The function of a noise gate is to reduce the amount of gain of a signal when it falls below a certain threshold. This reduces or eliminates any noise when the program signal isn't there, but allows the desired signal to pass through when it shows up as a strong enough signal.
So basically, if the signal drops below a certain level, the noise gate turns it off completely. Why would we need that?
Because it helps us get a noise-free signal. When the drummer plays the kick drum, there's an overring after each kick. A noise gate eliminates that and tightens up the sound.
Can you show us that?
Sure. Here's the kick without the noise gate. Can you give me that kick? And here's the kick with the noise gate. Go ahead and give me that kick.
Okay, so what's after the kick?
Well, after the kick, I'm going to work on the snare. I'm going to do basically the same thing. Adjust my input gain and my EQ. Go ahead and give me that snare.
So explain what you did.
I adjusted the input gain here and the EQ here. I went ahead and put a 3 dB boost at 2K, and I rolled out a little bit of the low end at 80 Hertz, because the snare doesn't really reproduce anything of that low frequency.
Okay, then what?
Well, next, I'm going to have the drummer play both the kick and snare together so I can get a balance and an even volume in the room. Could you give me the kick and snare together, please? Okay, stand by.
Okay, what'd you do, if anything?
Well, I didn't do all that much. I basically adjusted the volume in the room to balance out both the kick and the snare, since those are the primary instruments on a drum kit.
Okay, very good. What's next?
Well, next I'm going to work on the hi-hat. Could you go ahead and give me the hi-hat, please? Okay, stand by.
So what'd you do?
Well, first, I went ahead and turned on 48-volt phantom power, because I'm using a condenser mic to mic the hi-hat, and it requires that. Then I patted down the input 26 dB, because it's a pretty hot signal. Then I adjusted the input gain, and then the EQ. Here, I rolled up 3 dB at 8K, because I wanted the sizzle of the hi-hat. I cut 3 dB out of 80 Hertz, because I don't need the low end.
So no noise gate or compression on it?
No, a hi-hat doesn't need it.
So the toms are next?
Yes, I'm going to start with the high tom, then the mid tom, and then the low tom. I'm going to adjust the input, EQ, and noise gate for each of the channels. Then I'm going to listen to them in the room for balance and panning. Go ahead and play me your high tom. Okay, your mid tom.
kind of ring, man.
It's okay. And your low tom. Could I get all three toms together, please? Okay, stand by.
So explain what you did.
Well, first I turned on 48-volt phantom power for my first two rack toms because I'm miking them with condensers. Then I went ahead and adjusted the input gain on each. Now on the high tom, I went ahead and boosted 3 dB at 3K to get the good ring of it. And I also boosted 80 Hertz 2 dB to get a little bit of the good thud of the tom. On the mid tom, I boosted 2K 2 dB and 80 Hertz again 3 dB. Then on the low floor tom, I boosted 80 Hertz 4 dB and 250 Hertz 2 dB to get the thud and the rumble of a good floor tom.
What'd you do with the noise gates?
Well, I went ahead and set the noise gates to a threshold of -10 dB and a release time of 1/10 of a second.
Okay, so all that's left are the overheads.
Correct. First, I'm going to have him play both the crash, splash, and ride cymbals. Then I'm going to have him play them all together to get balance and panning in the room. Could I hear your cymbals, please? Okay, stand by.
So tell us what you did, Dave.
Well, for the overheads, I'm using condensers as well. So I turned on 48-volt phantom power first. Then I patted them both down 26 dB because you can get a really hot signal off of those cymbals. Then I adjusted the input gain and the EQ. Now for the EQ on both, I rolled off the low end at 80 Hertz, boosted 2 dB at 8K because I still want that crisp cymbal sound.
And you panned them left and right.
Correct.
Okay, what's next, Dave?
Well, next I'm going to have him play the entire kit so I can listen for balance and panning. Go ahead and play me the kit.
Dave, what about reverb?
Well, in this situation, I'm using 3 different effects. Now for a snare, I usually like to use a rich plate or a reverse gate. In this situation, I'm using a reverse gate.
How do you set that up?
Well, it comes out of the console on aux 5 into the reverb unit, out of the reverb unit back into a channel, which I have marked here, snare verb. Then I'm going to adjust the input and the EQ as necessary.
Great. Okay, what's next?
Well, next, I want to hear the bass player. Okay, stand by.
Okay, what'd you do?
Well, first, I turned on 48-volt phantom power because I'm using a DI to get the mic signal from the bass down to my front of house mixer. Then I patted down the input gain 26 dB and then adjusted the appropriate input gain. After that, I boosted 80 Hertz 3 dB and I also boosted 3K 2 dB. After that, I worked on the compressor. My compressor settings for the bass are a threshold of -10 dB, a ratio of 3:1, an output gain of 0 dB, and a peak limit of +10 dB.
Then you have the drummer and the bass player play together.
Yes, I want to make sure that the balance between both of them and the bass management between both of them is balanced in the room. Could I get you both to play? Stand by.
Okay, tell us what you adjusted.
Well, I didn't do that much. Most of it was for balance of the bass and low end in the room.
Okay, so now the guitar player.
Yes, I'm going to have him play a little bit, And the trick here is to try to get as much guitar into the main speakers as you possibly can.
As opposed to having it come straight off the stage.
Exactly.
Well, guitarists are notorious for wanting to be too loud. So what are some things you can do?
Well, one of the first things you can do is take the guitar amp and tilt it back a little bit, or turn it off access to the audience. And another thing would be to send a little bit of the guitar signal into the monitor, but be careful not to induce feedback.
Okay, so let's hear some guitar.
All right, can I get some rhythm guitar, please? Okay, could I get some lead guitar, please? Stand by.
Okay, explain what you did.
Well, I adjusted the input gain, and then I adjusted the EQ. Here, I took 8K down 3 dB. Then I boosted up 800 3 dB as well, just to get the nice warmth of that guitar.
So what about the keyboards?
If I take a submixer feed from a keyboard player, then I'm going to run it into 2 separate channels and adjust the gain for each.
Okay, what about EQ?
Usually, I leave it flat.
Well, let's hear some keyboard.
Could I get keyboard number 1, please? Okay, could I get keyboard number 2, please? All right, stand by.
So explain what you did there, Dave.
Well, first of all, I turned up the 48-volt phantom power because I'm running it from a DI. Then, I patted down the inputs 26 dB and adjusted the input gain. And I left the EQ flat.
So what's next?
Well, next I'm going to work on the vocals. I'm going to start with the lead vocalist. I'm going to have him sing something soft and then something fairly strong. I'm going to adjust the input gain, the EQ, and the compressor.
Okay, let's hear the vocalist.
All right. Could I get some lead vocal, please?
Whoa, 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 whoa.
Could I get something stronger?
Lights on, everybody. Won't you lend an ear? We know you came to party. We can make it happen here, yeah.
All right, stand by.
Okay, explain a little what you did.
Well, first I adjusted the input gain and then the EQ. I took a 3 dB boost at 3K and I rolled off 80 Hz 3 dB. My compressor settings here are -10 dB as a threshold, a ratio of 4:1, the output gain of 0 dB, and a peak limit of +5.
What about effects like reverb and delay?
Well, for my reverb, I have a simple plate reverb on the vocal set to 2.1 seconds and a delay set to 250 milliseconds.
Okay, so we've sound checked the drums, the bass, the keyboard, and the guitar, and the lead vocalist. So what's next?
Next, I'm going to have the band play a song at a fairly strong volume. That way I can hear what it sounds like in the room. And if I need to, I'll make any adjustments to the crossovers and the EQs then.
Okay, let's hear the band.
All right, guys, can I hear a song?
Lights on, everybody. Won't you lend an ear? You know we came to party. And we can make it happen here, yeah. Let's get loose. Get loose. You don't want to sit now, not when you can fly. Reach to where we're reaching. You can feel it if you try it. Let's get
Dave, this would be a great time to talk about compressors. What's the purpose of a compressor?
A compressor works to keep a signal like a vocal, which can be all over the place, within a workable dynamic range.
Why is that important?
Well, for one thing, it helps you control your mix by controlling the dynamic output of the instrument. There's a circuit within the unit called a gain reduction circuit. It reduces the amount of additional gain above the threshold setting by a certain ratio.
Can you show us how it works?
It's fairly simple. There's 4 controls. The threshold control allows you to set an input signal level above which signals will be compressed. The higher you raise this setting, the higher the level of the input signal before the compressor kicks in. The ratio control sets the compression slope. The slope determines how the output signal will change in relation to the input signal once the input signal exceeds the threshold. The slope is stated as a ratio, such as 2 to 1. The first digit indicates how many decibels of input change will cause a 1 decibel output change. A 2 to 1 ratio means the input level would have to increase by 2 decibels to create a 1 decibel increase in the output. With a 3 to 1 setting, the input would need to increase by 3 decibels for a 1 decibel change in the output level, and so on. Because the process of compressing a signal lowers the signal's overall level, there's a gain control, which allows you to compensate by adding output gain. The peak level control allows you to set a threshold for signal peaks. It basically helps prevent clipping by setting a certain threshold.
The amount of time the compressor takes to respond when the input level rises above the threshold is called the attack time and is usually fairly short, under 100 milliseconds. When the input level is above the threshold and then drops below it, the compressor will take some time to increase the gain. This is the release time of the compressor, which is generally longer than the attack time, possibly up to a second or 2. How's the compressor patched into the mix?
It's inserted on specific channels using an insert squid.
In a medium-sized PA system like this, what would you recommend for a minimum number of noise gates, compressors, limiters, that kind of thing?
I'd recommend at least 2 noise gates, one for the kick and one for the snare, and at least 2 compressors, one for the lead vocal and one for the bass. Also, a stereo limiter to protect your main speakers.
Okay, let's say a band's just getting started. What should they buy first?
If they own their own PA, then I'd at least get a stereo limiter to protect their mains, and 1 compressor for the lead vocal. And hey, you can get a lot of this gear pretty cheap if you buy it used. So I'd get it as soon as you possibly can.
So what about feedback? That's always a real problem for most bands.
Usually problems come between the vocal mics and the monitors on stage. Typically, singers like to hear it really loud. But when you have the monitors up too loud, it can be a problem. The first thing to do is make sure you ring the monitors out correctly. That'll go a long way towards allowing you to raise the gain before feedback. Secondly, if you're using a cardioid or supercardioid mic, move the wedge to the side of the vocalist so that the axis of the monitor is close to the angle of minimum pickup of the mic.
So knowing the pattern of the mic is important. Anything else?
If you have the luxury of 2 monitors per singer, you can set up a monitor angled at either side of the mic. Sometimes I actually sit the monitor up on something so I get it closer to the vocalist's ears.
Dave, as far as setting up the inputs on the mixer, do you group the instruments or label things in a certain way?
Yes, I label everything. I use tape and a Sharpie to mark all my inputs, my aux sends, and my effect returns.
As you can see, the sound check is a very important part of the process. If there are any technical problems with the system, this is where you want to find out about them and fix them. Same thing with the band. If they're having problems hearing themselves or getting comfortable with their sound, the sound check is where you want to solve those problems. Let's summarize what we learned. One of the keys to the sound check is to understand your mixer and all its functions. Before starting your sound check, double check these key functions: the phantom power switch, the mic line input, the pad, the pre or post fader position of the aux ends, the pan settings, and the fader position. Begin your sound check with the drums, starting with the kick, then the snare, hi-hat, mounted toms, floor tom, and overheads. You may want to review Dave's EQ and effect settings earlier in this segment. Set up a separate reverb for the snare. After the drums, work with the bass. Insert a compressor on the bass channel. If you're using a direct box, be sure to turn on phantom power on that channel at the mixer. Have the bass player and the drummer play together and listen to make sure the bottom end of the system sounds balanced and blended. Next is the guitar cabinet. Your goal here is to get as much of the guitar output into the PA as opposed to coming directly off the stage. You may have to adjust the speaker cabinet or increase the signal in the player's monitor in order to achieve this. For the keyboard player, typically the EQ is left flat at the mixer. The keyboard channels are panned hard left and right for each keyboard or for the keyboard submixer outputs. For the lead vocalist, set up a compressor through an insert on the channel and have the singer sound check at a soft and a hard volume. For vocal effects, try using a separate reverb and delay. In order to increase the gain before feedback of the stage monitors, be sure to ring them out and place them at the angle of minimum pickup of each microphone. You can also raise them in this position. Finally, have the band sound check a song at fairly strong volume in order to get the monitor set and to determine how much volume will be coming from the stage versus through the PA. Remember, the more on-stage signal you can put through the PA, the more control of the total output of the band you'll have at the console. The goal of the sound check is to hear how the band sounds in the room and compensate for any acoustical problems and problem-solve any system-related issues. You'll always make a greater impression on your audience if the band sounds good from the very first song instead of struggling with feedback and a poor-sounding mix. Dave, before we wrap this section on the sound check, I want to ask you a very important question. What would you do if you simply didn't have time for a sound check?
Always do the vocals first. Make sure that they're up and working as soon as possible.
So the vocal is the most important thing?
Definitely. After you've got the vocals, then work on anything else on the stage that doesn't have its own amplification, like the drums.
Okay, so anything else about the sound check?
Yes. Always remember to turn the reverb and the delay off in between songs.
You heard it here. Okay, the sound check's done and we're ready to mix. But before we do, there's an important subject we need to cover. Something every sound engineer will be forced to deal with at some point: electrical problems. When we return, we'll show you what's up with system noise and a few tips you can use to overcome those annoying hums and buzzes. We'll be back for more of live sound reinforcement after this. For your review, here are Dave's sound check settings.